Line chart visualization is a very common visualization technique. It plays a crucial role in time series analytics, where it is generally considered the most effective visualization approach. On the right we show three line charts, which represent some typical time series data. The uppermost chart shows the speed of a football in a soccer match. In the middle, household power consumption for a period of 2 weeks is shown. And the chart at the bottom portrays some random noise. To effectively explore such time series data, interaction proves to be key. This is emphasized by both Schneiderman's visual information seeking mantra and the zoom plot methodology. Interactive visualization is necessary to provide an overview, enable zooming and filtering, and allow access to details on demand. However, interactive visualization is challenged at large data volumes. On the one hand, each interaction results in rendering an updated view of the data, which requires a fast rendering solution for such large amounts of data. And on the other hand, interactive visualization tools are typically purely front-end based, meaning that all data is stored in the front end, which limits scalability due to latency issues and client-side limitations. It is thus clear that scalability is key to realize effective line chart visualization. One approach to realize scalable and interactive visualization is through data aggregation. LTTB stands for the largest triangular tree buckets and is arguably the most widely used data point selection algorithm for line chart visualization. It aims to maximize the local triangular surface spanned by selected points. On the right we show a new column displaying the downsample time series using LTTB. For the ball and power consumption datasets, little to no difference is noticeable with regard to the reference visualization. For the noise data, however, we observed that some local minima and maxima are not selected by LTTB. This can be attributed to LTTB favoring binwise alternating extrema to maximize the local surface area. It is thus clear that LTTB provides a quite good approximation of the reference visualization with very few data points. However, although LTTB is widely adopted, it possesses some unfavorable computational properties which limit its applicability to large data volumes. In particular, it requires a sequential pause of the data which hinders parallel execution, and it involves expensive triangular surface computation for each data point. To address these unfavorable computational properties of LTTB, we propose a novel algorithm called MinMax-LTTB. MinMax-LTTB is a two-step algorithm that is an extension to LTTB. In the first step, it applies MinMax-Preselection. For each bucket, several vertical extrema are pre-selected. In the second step, LTTB is applied on these pre-selected vertical extrema. Since only the first step scales with the length of the data, MinMax-LTTB possesses the same computational properties as MinMax. This means that it is computationally efficient as MinMax only entails comparisons, and it provides parallel execution just like MinMax. Analyzing the visual representativeness of MinMax-LTTB, we observe that it is highly similar to LTTB. In the first two rows, we notice no clear difference between MinMax-LTTB and LTTB, and in the last row, which represents the noisy data, we remark that MinMax-LTTB tends to even slightly better approximate the reference than LTTB. This can be attributed to the fact that MinMax-LTTB only considers extrema when applying its second step, whereas the vanilla LTTB algorithm considers all data points. When benchmarking the single core and the multi-core execution of the MinMax-LTTB algorithm and comparing it with LTTB, we notice two things. First, the single core execution is up to 10 times faster than LTTB. This can be fully attributed to the reduced triangular surface computation. And secondly, the multi-core execution is even up to 30 times faster than LTTB, allowing to downsample 1 billion of data points in around 0.1 seconds. In summary, MinMax-LTTB proves to be a faster alternative to LTTB that has highly similar visual representativeness.